All right. A linear equation is when a constant increase, an add or subtract and change in one variable is associated with a constant add or subtract in the other. So let's write that down. When a constant increase or decrease in one variable yeah, that's fine, is associated with a constant added or subtracted amount in the other. So in our first equation, we had plus 5, plus 5, plus 5, plus 5, and it ended up being a linear situation. Sorry. Okay, so here's what I mean. Our pattern, plus 5, plus 5, plus 5, plus 5, ended up with an image that was a straight line. So we call that our linear equation. Constant increase in one is associated with a constant add in the other. And then for exponential, well, that has the word exponent in it. And so this is when a constant increase or decrease in, let's write that down. When a constant increase or decrease in one variable, and I really mean the independent variable or the explanatory variable there, okay, is associated with a constant, constant percent change, or in the other, or as I would like to put it, right, a constant multiplying factor or division factor in the other. All right, let's take a peek at example 5, the last example in these notes. This comes from your textbook, the Mercer and Sebecki book, on page 48. You deposit $1,000 and the bank adds 5% of $1,000 each year. That's called simple interest. You deposit $1,000, woohoo, and the bank adds 5% of the account balance each year. That's called compounding interest. Fill in the table to compare these two accounts. Okay. Right. Let's see here. I'm going to start with the first account, and it looks like they've already filled in after 1 year. That must mean that 5% of 1,000 is 50, and that is getting added every year. The bank adds this amount each year. Okay, so this is going to be easy. Just add 50 every time. 1,100, 1,150, 1,200, 1,250. And, right, this is just a constant add 50 business. Okie dokie. Just to check that. Let's see, so 5% of $1,000. I trusted them at first, but I'm thinking maybe it would be nice to show it. 5% is 5/100ths. That portion of 1,000, okay, really is 50. We're good here. Now in this account 2, it's 5% of the account balance each year. So now we're not doing 5% of 1,000 again. For the next year, for the second year that this is sitting in the bank, we actually are taking 5% of 1,050. So 5/100ths of 1,050, and that is going to be added. Okay, so let's see. 5% of 1,050 is $52.50, but I'm adding that to 1,050 that's already in the account. So I end up with $1,102.50. Okay, let's write that. $1,102.50. Got it. And then I'm going to do this again. 5% of $1,102.50. Okay, let's see what we got here. Times 5%, and then add that to $1,102.50. 1,157.63 about. I never like to say that a bank would ever give someone money that isn't theirs, but what are you gonna do? $1,157 and about 63 cents, but really just under that. Yeah. Okay, and then I would continue this pattern. So I keep doing this in my calculator, doing the 5% of what came before and adding that amount. And let's see. I end up with $1,215 and about 51 cents. And then I end up with $1,276 and about 28 cents. So just following that pattern all the way down. And I had to use my calculator to do this, but nonetheless. Oh, I see a typo. Both accounts compute the same amount after 1 year with a grand plus 5% of a grand. Use the distributive property to fill in the blanks. Okay, well, it looks like the distributive property had happened and multiplied some number times the 1 and times the 0.05. Well, that number was 1,000. 1,000 times 1 is 1,000, and 1,000 times 0.05, there it is. Oh, and then here it looks like they just added 1 plus 5/100ths. So this is still 1,000. Got it. What pattern does account 1 follow? Well, I noticed right here, I actually had already used that pattern. Plus 50, plus 50, plus 50 in order to generate all of those numbers anyway. So the pattern I see is linear, and I see add 50 each year. And then in number 2, oh, this one's a little bit harder. But I think they gave us a hint right here that in addition to just adding, maybe we could multiply this to get 1,050. So I went through and I tried this multiplier. So 1,000 times 1.05 is 1,050. And I would go through and check this times 1.05 every time. And I believe it'll work. So if you don't believe me, I went ahead and checked it because I just have to. So take your amount and then multiply it by 1.05, and it should come up with the next amount. Okay, so it's definitely exponential because it's a constant multiplier. And that constant multiplier is, so for every increase in a year, so for every 1 additional year, we are having a constant multiplier of 1.05. Whoops. That is supposed to say year. Got it. Account 1 is computed using A equals $1,000 plus 50 added n times. And account 2 is computed using the formula A is a grand constantly multiplied by 1.05 n times, where n is the number of years after the deposit. Find and compare the amounts after 20 years. Immediately I see this, and I tag it with an n because n is the number of years. Okay, I'm going to call this A1 for account 1 so that I don't actually have to label it account 1. So I'm just being lazy and calling this A1. A1 will equal $1,000 plus 50 added 20 times. Well, 20 50s is 1,000, so we would end up with $2,000 in account 1 after 20 years. Okay, in account 2, we would start with $1,000, and that would be multiplied by 1.05 20 times. Repeated multiplication. And that I definitely have to put into the calculator. Okay. 1,000 times 1.05, that was multiplied by it 20 times. $2,653.30 about. So approximately, and so you notice that there is a difference in my opinion from exact equals to a rounded or estimated equals, like where we're waving our hands. $2,653 and about 30 cents. Okay, after 20 years. So a quick summary of what we just did in this whole section. Okay, we really were comparing lines and exponentials. I dropped it on the floor and accidentally rolled over it with my chair. We were comparing lines and exponentials, and we really had to use equations and expressions and solutions and talk about all of that language in order to be able to create our equation that matched our pattern. And then we looked at these patterns. A constant rate of change or a constant addition, that ended up being linear. And a constant percent change or a constant multiplier, that ended up being an exponential. And we gave them these names because the linear pattern, which was plus 5, plus 5, plus 5, gave us an image of a straight line, and its equation looked like something like this. We gave the exponential pattern, or the constant multiplier, this equation, which looked like this instead of like a straight line, so it had a curvature curving up, because it had, so even though it doesn't stay at here and it's a constant percent change or a constant multiplier, we know that when we are constantly multiplying, it affects our exponent, hence the name exponential. So we really took a pattern and we wrote an equation to kind of model that pattern. And then we were able to use those patterns in order to find out, I mean, we have some data, we know some data we can get, and we can create some data, but in the end, can we kind of predict what will happen? And that's what we use this to do.